All right, so we talked about binary coded decimal, right? So we talked about representing numbers, and particularly large numbers, in binary, right? And we said that instead of just reproducing the same number, the same decimal number in binary and ending up with a number with lots of bits, right? Uh, what we tend to do is that we tend to translate or map each number, each digit from the decimal number into binary separately, right? And that what essentially binary coded decimal is, right? But binary coded decimal is also going to be very useful for our next topic, which is ASCII, right? So the need for this is that, so we already got our numbers translated. What about our alphanumeric characters, right? Our I mean ABC and I don't know, special characters and things like that. So for that there is this mapping which is called ASCII, right? And it is an acronym for American Standard Code for Information Interchange. Yeah? So what is there in ASCII really? Let's talk about it first. So it's widely used in computers, like it's all over. We're going to talk about it, not just ASCII, but there is an extension of ASCII in a way, right? We call it Unicode. We're going to talk about it later on. But ASCII is used a lot, and it is used in keyboard characters definitely, and some control characters as well. Right. So all of your alphabets and special characters, all of these are definitely covered. These are the ones that we are the most concerned with, right? There are some other control characters, right, and reserved characters as well, but that's not our concern at all. Okay, so Unix and DOS based systems, right, they use ASCII as well for text files, right? And we either have a 7-bit code in it, I mean 7-bit numbers in it, or we have 8-bit numbers in it. So both of them are there. We're going to talk about it. But 7-bit code is the one which is definitely the standard one. 8-bit is there, but that's sort of an extension to the standard one. So we'll keep talking about it. But 127 is the the maximum number that it can support, right? So remember that. How do we find the maximum numbers that can be supported? So we would take something like because we are talking about 7 bits here, so 2 to the power of 7 minus 1, okay, and that would be equal to 127. Okay, so that is how we find out, and it supports up to that characters. The 8-bit, it is used as a verification sort of number, and then there's an extended ASCII which makes use of the 8-bit formulae. Okay, so here's a table which tells us about ASCII. So for example, the number 65 in decimal, right, and in hexadecimal it is equivalent of 41, right, in octal it is equivalent of 101. So this is what the character A, uppercase A, remember there is a clear distinction between them, they are not the same, right? So uppercase A is represented that way. Yeah, so the hexadecimal number 41, right, represents the character A, or in decimal terms we say it's 65, right? Um, but in terms of ASCII, right, it's a 7-bit ASCII, and it makes use of the binary coded decimal. So 4 is represented by this 100 here, right? So it's the third bit that is on, and third bit represents 4, as we know, right? And then the first bit is on here, so that just represents 1, right? So 1, 2, and 4, right? And then there's 1, 2, 4, and 8, but just the first one is on, so that's 41. And so on. So we have all of our characters moving on from A to N, right? Starts with 65 decimal and moves on. And lowercase alphabets start with 97, yeah, and they move on from there. So you're not in any way supposed to remember all this, right? But just so that you know that how we really represent all of our characters or special characters or alphanumeric numbers in here, right? So we represent it by using some sort of encoding, right? And ASCII is the one we use here, right? So let's look at this link. It's ASCIItable.com, right? So it in detail talks about ASCII. So here we are, all of the numbers represented, and of course they're represented in decimal, hexadecimal, and octal at the same time, right? So all of these characters, if we start from 0, are not relevant to us, right? The description of it is given here. Not all of them are relevant to us, but the ones that are relevant to us, they start somewhere from here, so from space, right, from the decimal 32, so space and then exclamation mark and all this, because they're useful to us, and then uh, the numbers from 0 to 9, right, they start from 48, goes down to 57, and our numbers, which is like uppercase alphabets, they start from 65, and it ends at 90, and then the lowercase starts from 97. Yeah. So here this is. We're also going to talk about extended ASCII, right? So what extended ASCII does is that, so let's start, the standard ASCII starts from 0 and goes until 127. Yeah. So here it is. We are starting from 0 and going on till 127, and 127 is the maximum we can represent with 7 bits. Yeah. Remember 2 to the power of n minus 1, right? But if we look here, in extended ASCII, what we are really doing is that we are just making use of the 8th bit as well. So just including the 8th bit just actually doubles it, right? So it doubles the capacity we have. So now we can also map from 128 to the maximum of 255. So many more special characters, right? And some mathematical terms as well, right? For example, there's a half here, right? These were also represented. So 171 decimal is represented by a half, yeah, 1 over 2. And similarly, omega and all these mathematical symbols are also represented. So we have to make use of the 8th bit as well for this. So ASCII comes in two forms, 7-bit and 8-bit, right? When the 8-bit is included, we say that is an extended ASCII code. Okay, so next we are going to talk about EBCDIC, right? And it is an acronym for Extended Binary Code Decimal Interchange Code, right? It has, code 2 times. So this is very similar to ASCII in the sense that it also translates, special characters and some of the um, alphabets, right, from binary into, um, um, so it represents it. So it's very similar in that sense. But what is different is that it was mainly used by IBM mainframes, right? So IBM was sort of a proprietary. It was their proprietary uh, um, technology, and they were just using it, and that is why its use were a lot before, when computers were primitive in the 1970s and 80s, right? But now it is not used so much, right? But I do have a link that is in the course notes for you, so I would suggest you go look at it. So it tells you all about it. But the main difference is that it is really 8-bit, and it's always 8-bit. So we just discussed ASCII, and ASCII was, the standard ASCII was 7-bit, and the extended ASCII was 8-bit, right? 8 bits. But so EBCDIC is always 8-bit, right? That is something we need to know. Right, so we're going to look at some of the differences between EBCDIC and ASCII, right? Um, so I explained the first one. So it's 8 bits, and ASCII can be 7, right? And then it was changed to 8 when it was extended, right? Um, so because initially EBCDIC was always 8 bits, right? So it started with 8 bits, so it had more characters. It could map up to 255 characters, while ASCII was limited to 128 characters. But that limitation or that difference is no longer there, because now both are 8 bits, right? there's one more difference, and it's like the ordering of letters, right? So uh, from A to Z, how it was ordered. So in ASCII, it is numbered, and the numbers are linear, right? Uh, um, but in EBCDIC, it is a bit different, right? So they represent from A to up to 9 more alphabets, right? And then it stops, and then it moves on again from 1 to 9, right? So to simplify it, we would have about in EBCDIC, we would start from A, we would move till I, right, until the ninth alphabet, and then it introduce some more uh, characters, some different characters other than alphabet, and then it would again go from 9. So it would only deal with 9 alphabets at a time. Unlike ASCII, if it starts mapping the alphabets, so it doesn't stop it, it doesn't finish it until all of them are done, right? So this is also something to keep in mind. It was a big of an issue initially for programmers to understand this, and it wasn't so intuitive in the sense. ASCII was more intuitive, right? So you started from A and went on till Z, continuously, right, in linear ordering. So that's another difference. Another thing is that ABCDIC isn't really compatible with some of our modern encodings. For example, Unicode, right? Unicode is something we're going to be talking about after this. But we need to know that ASCII is compatible, right? So EBCDIC, you can think of it as a technology that is not so much used anymore, right? And it wasn't even maintained that well, right? And it wasn't also um, sort of the updates were not issued on time. There were if there was any problem. So for that reason, ABCDIC is no longer used as much. So we will keep in mind that it is still used in IBM mainframes, some of them IBM servers, but in general, is pretty much obsolete in that sense. Okay, so next up is Unicode, right? So Unicode, what we mean by it is universal coding, right? So that is sort of a combination of these two words. Um, and what it is really is that it's just a way to assign numbers to many more characters than we can do with ASCII, right? So ASCII, in fact, extended ASCII has 8 bits. In 8 bits, we can represent a maximum of 255 characters, right? So we are done with English, right? So we are done with uppercase alphabets, lowercase alphabets, right? But what about other languages, right? French, for example, right? Or Chinese, right? Or any other language, they would have uh, different kind of constructs, right? And that would be a problem. So and we are done, right? In ASCII, we have utilized all of our mappings, right? Which we could do, which was 255 at maximum, and that is why the need for Unicode really came in. And Unicode was able to solve this problem, right, by sort of taking the limit uh, um, out of the equation here, right? So there's pretty much no limit in case of Unicode. We can have UTF-8, we can have UTF-16, right? So UTF is represented by Universal Character Set Transformation Format, right? So that's U, T, and F, right? So we have 8 and 16. So when we say 8, we mean 8-bit Unicode, right? And when we say UTF-16, what we mean is 16-bit Unicode. Um, we're going to talk about the differences in these further when we compare it with ASCII, for example. But do keep in mind that 8-bit is the most popular one. It is the one which is most widely used, right? In fact, it is used in more than 50% of web pages, right? So there was a statistics about it, which basically stated this. We have 16-bit as well, right? We talked about this. So 8-bit Unicode in general, and in particular the 8-bit. which is UTF-8, is the standard practice these days, right? So any new internet email, XML files, HTML, all these things, you'll see they are encoded with Unicode. So if you want to see that all the different kind of characters that have been mapped with Unicode, you can go to this link, right? So I've given it here. If you click on it, let's see. So here it is. We have all these different type of characters. So we have started with all zeros, right? And then moving on, we have so the first 10 here, right? It's represented in hexadecimal, so we are starting from 0 and going till F, 16 characters. And so here it is. Of course, the first set of characters is very similar um, to ASCII, right? So that is a very important thing to understand, right? So Unicode is basically extension of ASCII, right? So all the characters that were in ASCII are also there in Unicode, right? But there are some additional ones there. So so here are all the numbers going from all the alphabets from A to Z here, and then the lowercase from A to Z, and they have the same kind of hexadecimal equivalence or decimal equivalence, right? So it's basically the same. And that is very good because it was compatible with the ASCII, which was the norm before Unicode was popular, right? So if we look at it, we have so many more characters. See this? So we have incorporated a lot more languages into it, right? We can it just goes on and on, right? So look at all these kind of mathematical symbols, and then we have the um, characters from all these languages, right? And it just moves on, right? So this we have Hebrew here, Arabic here, right? And it moves on. So if you want to look at the Unicode mapping of a particular language, you can always look at it here, right? So I don't know if I would like to maybe search for French here, FRENCH. Okay, I can't seem to find it here. Um, it looks like it is, no, it's not in alphabetical order. I thought it would be in alphabetical order. But anyway, the point being that pretty much all of the languages that are known that are mapped here, and it just this list goes on and on, and new languages and even existing languages that have not been included in Unicode yet, constantly work is being done to include them. So so this is a nice website for you to look at if you want to know more about Unicode. Okay, so here we have a sort of comparison between the two kind of encoding methods, right? So ASCII and Unicode. Unicode is currently pretty much the standard, right? It's the industry standard for consistent encoding, right? And it is used to encode text, especially. Okay. There's another thing to know about Unicode. It uses something called a variable bit encoding, right? Variable bit encoding would mean that it would use the number of bits that are required, right? So if there are more, I mean, in your document, for example, there are more languages and characters for different languages included, right? So it might move on to 16. Otherwise, it would stay at 8 characters, right? 8 bits. So that is something to know because the number of bits that are there are not fixed, and they are variable. They can sort of be increased based on if there is use for it or there is demand for it. So that's something very interesting about Unicode, and that makes it so much more usable, right? Than the other kind of encoding formats. Okay, so we also going to talk about oh yeah, so I was looking at these statistics, and I found out that currently there are about 34,168 distinct coded characters, right? So look at this, that's just a lot, right? Characters that are there. So they are from various languages. Yeah. So that is something interesting to know. So if you compare it with ASCII, in ASCII, as I said, there are just 8 bits, right? It started with basically 20. It started with 7 bits, which means it could represent a maximum of 128 characters. In that case, the 8 bit was just used for as a check digit, right? As a sort of an extra digit. We didn't really have a purpose, and they intentionally did it because at that time, when the 7-bit ASCII was being used, that was the pretty much the start of the computer age, and at that and for that reason every bit of memory was very important and was very sort of scarce, right? So they had to very wisely use it, and for that reason they were not using the 8th bit because it wasn't so much needed to represent our basic alphabets, right? And that was the reason behind it. Now when I think about it, things have changed so much that even if you're programming, you don't really think about these things, right? If you're declaring an integer, you might just declare a 32-bit integer, right, or 16-bit integer, knowing that maybe your value will never exceed even, let's say, 4 bits, right, or 6 bits, but you would still declare a higher number of bits for it because the memory is easily available and is so much cheaper now that we don't really think about it. But that's it. So they started with 7, and then when there was need for it, they extended it to be 8 bits. Right? We're talking about ASCII. Okay, in extended ASCII, 256 is the maximum number of characters that can be represented. Okay, so I think I've mentioned it before, but I think it's important to mention again. That for every character that ASCII has a value, Unicode has the same value for it, right? So in other words, Unicode is an extension of ASCII. Okay, and that's an important property because it makes it back compatible, right? So any documents that had ASCII encoding, Unicode was still able to open it, right, and work with it and process it, right? Um, all right, so we are pretty much done with the different kind of encodings, but I thought it would be interesting to also include IPs in here, right? Um, if you know what an IP is, so it's representative Internet Protocol, and what it's just basically an address for every device that that's on internet, right? And it's unique, of course, right? um, of course, if it's an internal network, if it's a local area network, it doesn't have to be unique. But so we have the concepts of private and public IPs and everything like that. I'm not going to go into that, but what I really wanted to mention here is that um, when we look at an IP, um, it's really binary, right? Before, when I didn't know much about binary, I still was using IP, but I didn't really think about it. I didn't think about it that why the numbers can never go more than 255. 255 is always the maximum that can be represented. I never thought about it in that case when I didn't know about binary and number systems. So now when I do, it's really interesting. So in IP, we see we really have um, 4 sets of uh, 8 bits each. So we really have 4 bytes, right, in an IP address. Uh, and in total number of bits, we have 32 bits here, right? So 8, and 8, 32 bits. Okay, and that is why the numbers in an IP address, they never go above 255 because every set is basically a byte, and a byte can never go above 255 in decimal, right? So this is what we have, and although what we see is this, but computer always uses the binary version of it, right? Which would be this. So 184 in binary, right, would be this number, right? So 10111 and 000, right? So 14 would be this. So the second bit on, the third bit on, and the fourth bit on, right? So that's 8, 2, sorry, 8, 4, and 2. Yeah, so there you go. That's 14 for you. So so also I was thinking about the maximum number of um, the maximum number of IP addresses that we can have with 32-bit. Yeah. So 32-bit is the same as IP version 4, right? So IP version 4 is made of 32 bits. So if you think about it and use the formula, which is 2 to the power of n minus 1, the minus 1 is just not significant here because we're pretty much estimating. We don't want the exact number. So 2 to the power 32, that, because we are, remember, we are exponentially growing, right? So 2 to the power 32 is equal to about 4 billion IP addresses. 4 billion, right? So that's a huge number. But guess what? It's an interesting story, because 4 billion addresses turns out are still not enough to give IP addresses to satisfy the needs of IP addresses that we have in this age, right? And for that reason, we needed more bits, and that's why we have something called IP version 6 now, right? And what IP version 6 does is that it just gives us far more bits to work with. Yeah. So now we have 128 bits, right? 128 bits would give us a huge range, a huge range. So 128 bit would be equal to 3.4 with multiplied by 12 to the point 38. So that's your scientific notation. That's about 340 undecillion IP addresses. That's just a huge number. It's just not easy to sort of get your head around it. But think about this. If you have IP version 6 and you want to assign about 4 billion addresses, which means the whole range that IP version 4 can give you to every person on alive on the planet, on Earth today, right? You will still have far more to work with, right? So just to repeat that, this number 340 undecillion, that is such a huge number, right? That is such a large number of IP addresses that if you were to give 4 billion IP addresses, right, to every person on the planet today, right, you would still have a lot more to work with, right? So that's just mind-boggling. All right, so we move on to digital technology metrics, right? Metrics. So this is just really for you to understand that how memory works, right? So this is how it really works. So we have in a bit, right? A bit is just, it can have two states at the maximum, right? It can either be on or off. We have discussed this. 8 bits when combined they form a byte. Yeah. So and then when you have 1024 bytes, right, they combine to give you a kilobyte, right? But this is an important distinction because kilo in I mean standard measurements would mean 1000, right? But because we work in the exponents of 2, right, it is important to note here that in terms of computer memory it is not true, right? A kilo would not mean 1000. I mean, it's a good approximation of it, but a kilo, to be specific, it would be 1024. Yeah, in computer terms. So we have 1024 bytes, and they combine to give you a kilobyte. Then when you combine 1024 kilobytes, you get a megabyte. Yeah. And when you combine this many megabyte, right, the same amount, you have a gigabyte. And when you move on, you have then a terabyte, we have a petabyte, we have an exabyte, right? And it really moves on. It keeps on going. But it is something interesting to know. So just like a kilo would refer to 1,000 in general, but in computer terms it means 1024. So similarly, a mega, right, refers to 1 million, right, in general terms. But in computing, uh, it really means this many bytes. Or in other terms, that is 2 to the power of 20. Yeah? Or if you multiply 1024 by 1024. So if you want to know more about these digital technology metrics, I would suggest you go to this link. This is a pretty nice one. It's pretty detailed, right? So it talks about, in fact, that chart, I had taken it from here. It talks about all these memories, and then it moves on. It talks about the computer speed as well, because this was one of our topic that was covered last week. So it's important to know these things as well, how the speed works and the data transfer rate, right? So there are many charts in here. I encourage you to look at it. They're pretty interesting. Okay, so we are pretty much wrapping this up. So um, let's look at a few examples of what we have done so far. So here we look at a question which asks us to convert 12 GB into MB, right? So that should be pretty simple, because what I have to think about is that how many MBs are there in a GB, right? How many megabytes in a gigabyte? And as we have just looked at in the chart, right? So in a gigabyte, we have 1024 megabytes, right? So that means all I have to do is would be to multiply 1024 by 12, right? And I would have my answer in megabytes. Okay, so that's as simple as that. I can do this. I'll just use a calculator for it. Um, so let's do this. 1024 multiplied by 12, right? So the answer for this would be just simply 12,288. Okay. Okay, so I'm just going to minimize this. And the second question asks us about IP address. So we have been given an IP address, and that's of course in binary form. Sorry, that's in decimal form, and we have to convert that into binary form. So all we have to do is just to think about it, and we have to convert the individual set of numbers into binary, right? So 95, you know the process. You just have to convert that into binary, right? So 189, 1108, and 202. You're going to convert each of them separately, and then you're just going to write it with a dot between them. Okay. So if I have to do this, I will just use a calculator for this. I would go to the programmer function on my calculator. I'm gonna put decimal. I'm gonna click on decimal, because the number that I have, the source, it is in decimal, right? So I'm gonna write 95, right? So as soon as I enter 95, I have the binary. Yeah. So that's the binary. I'm going to write this, then a dot, and then the next one, which is 189. So 189. So I have the binary for this as well. It's right here. Okay. So I'm going to write all four of this with a dot in the middle, which is a separator, and there you go. This is done. Okay. So moving on, the third question, we have been given speeds of computer, right? So we have 1234 megahertz, and we've been asked to convert it into gigahertz, right? So this question is very similar to the gigabyte to megabyte question. We just have different units to work with. One is about speed, the other one is about memory. Okay, so I have to think about it in exactly the same way. I'm going to think I've been given it in megahertz, right? And I have to convert it into gigahertz. So how many megahertz are there in a gigahertz, right? And there are 1,000. Yeah, there are 1,000 megahertz in a gigahertz. Okay, so how will I convert it? All I have to really do is simply take the decimal place. So the decimal place is here, right? In any number, it's here, and I'm going to shift it 3 places, right, to the left, right? So I'm going to say 1, that's 2, and that's 3. So 3 places. So it's going to become 1.234, right? That's it. That's simple as that. So 1.34 gigahertz. Okay. So if I give you another number, let's say 3.5 um, gigahertz, I give you in gigahertz, and I ask you to convert into megahertz, right? So all you have to do is to because now we're really reversing the process, so we have to move 3 places to the right, right? 3 decimal places to the right. So I'm going to say 1 place, 2nd place, and 3rd place. Yeah. So in other words, this is going to be, so we have empty space here, we can fill that with a 0, right? So this is going to become 3500 megahertz, right? So we just converted it from gigahertz to megahertz, right? So this is how really the conversion works, right? So we are done with this one. Okay, so as an interesting problem, I have a message for you right here, and if you can decode it, right? So it's encoded, and if you can decode it and tell me what it is, that would be really nice. Okay, so I have a message for you right here. All right, see you then.